I'd like to have us look at one additional example from 16.2, just to kind of summarize what I said in the lecture. I want to look at one example that could be asked in one of three different ways. It's the same problem, but asked in three different ways. So you could be asked, find the work done by a given vector field in moving an object along this curve, this helix, for t goes from 0 to pi. You might be asked, compute f.dr with vectors for this vector field when this curve. You might be asked, compute this integral here in differential form for this curve given parametrically. All these are the same question. So what I want to do is just show you how you would work each of them. These two are both vector form. So these two are done in vector form. And this one is differential form. So if we work in vector form, then work, which is also this integral, okay, that's the book's notation. I like to write what it really is, which is taking f dot the unit tangent and doing a line integral with respect to arc length. That's what we're actually doing. The shortcut for that is that we do f dot r prime dt, and t goes from a to b. So we actually end up doing this line integral as an integral of a function of one variable. So we kind of lose sight that it was a line integral. Okay, so in order to do this, I need f in terms of t, and I need r prime in terms of t, and then I need the dot product. So f in terms of t. So f is x, y, comma, xy. I tend to write the vectors in this notation instead of ijk. Now I need to get that in terms of t. And I do that by using this curve here. This is my x, whoops, this is my x, this is the y, and this is the z. So putting in for x, whoops, that's not x, and putting in for y, and there is no z to substitute for, so we would get x equals cosine t, y equals sine t, and xy equals cosine t sine t. So there's f as a function of t. I need my r prime. So if this is my r prime is minus sine of t, cosine of t, 1. So the dot product, f dot r prime, all in terms of t, equals, we're just dotting, cosine times minus sine, sine times cosine, cosine sine times 1. So minus cosine t sine t plus sine t cosine t plus cosine t sine t, which equals cosine t sine t. Right, so that becomes our integrand here. And so we get that the work or f dot dr, just playing with the notation there, is the integral from 0 to pi, that interval was given, of cosine t sine t dt. That's a straightforward u substitution. And so I get u du When t equals 0, sine of 0 is 0. When t equals pi, sine of pi is 0. So 0 to 0, that's 0. Okay, that's using the vector form. If we do this in differential form, you're going to see that you're going to do exactly the same computations. It's just the notation is different. So if I'm going to compute this in differential form, I have x dx plus y dy plus xy dz. And we're going to put in for the x and the y here, x and y. So we're going to put in the x and y as we did before. So x and y. Now for the differentials, for dx, that becomes dx dt, dt. dy becomes dy dt, dt. And dz becomes dz dt, dt. And as we saw when we were doing section 16.2, the first part, we put these all in here, and then the dt, we just factor that all the way out to the right so that we have one integral with respect to t. So we get x, which is cosine t, dx dt, so dx dt is the derivative of cosine, so minus sine of t. So dx here is dx dt dt, which is minus sine of t dt, and as I said, we end up just factor that dt out. Y here is sine of t, so sine of t. I'm going to multiply by dy, which is dy dt, so derivative here is cosine, so cosine t dt, which is already factored out here. This is z, z is t, so dz dt is 1. So here we're going to have x times y times dz dt times dt. So x is cosine, y is sine of t, and dz dt is 1 dt. And t goes from 0 to pi. And so we get minus sine cosine plus sine cosine. So those are gone and we're left with cosine t sine t. So you should see the similarities between the expressions that you get. You're going to get the same thing. It just sort of feels a little different how you got there. Here's vectors and dot product. Here you're using differentials. At any rate, you're going to end up getting the same answer. So just wanting to point out that these work problems sometimes are going to be asked as find the work. Sometimes it's going to be asked as a line integral in vector form. And sometimes it'll be asked in differential form. If they ask in differential form and you'd rather work in vector form, then you can work in vector form. You just have to know that they're equivalent. Same here. Maybe you would rather work in differential form than vector form. You just have to know, once again, that they're equivalent, and you have to know whatever way it's asked, you have to know that it needs to be done one of these two ways.